Good afternoon, Bulldogs. I promised that we would talk later about the Z distribution and converting or transforming other distributions into a Z distribution, and then how to use the tables and how to find probabilities without the R software. So that's what this video is all about. Let's first remind ourselves what the normal distribution looks like for mean mu and standard deviation sigma. See the mean in the middle and the standard deviation is a measure of its dispersion. The standard normal distribution, that is the standard normal 0, 1 distribution, is a specific normal distribution. And the units on the horizontal axis of the standard normal curve are actually denoted by Z. And a specific Z value gives you the distance between the mean and the specific point represented by the Z value in terms of the standard deviation. Now recall that the area under a standard normal curve has something to do with probability, and we talk about it from left to right. So if we wanted to know what the probability of a value, say this or less, so this A, we would be interested in the area of that shaded region. Now, suppose that A is like this up here says, Z equals 1.95. So the tables that are on page 464 and 465 in your text are similar to what I'm showing on the screen right now. And you find the Z, so you look at this, we want Z of 1.95, and in our case, we're gonna have to go over to the positive side, but you follow the line down the left, and to find 1.9 and then 1.95, so the second part of the second place of the decimal, find that on the vertical axis, and where those two meet is the probability we're interested in. So that area to the left is 0.9744, meaning that if whatever this line represents or less is 97.44% probability of occurring. What if we were interested in 1.95 or greater? Remember that the area under the curve totals 1. So if we subtract the green area from 1, we get 0.0256. That's the probability of 1.95 or greater. It might be useful to compare two different random variables that happen to be on different scales, like the SAT, ACT example from the text, or if we need to understand the probability of a random variable that happens to be normally distributed, we can use the Z score or a Z transformation to understand it in terms of a normal 0-1 scale. Let's do an example. According to the Kaiser Family Foundation, U.S. workers who had employer-provided health insurance paid an average premium of $4,129 for family coverage during 2011. Suppose that premiums for family coverage paid this year by all such workers were normally distributed with a mean of $4,129 and a standard deviation of $600. Find the probability that such a premium paid this year by a randomly selected such worker is between $3,331 and $4,453. The first step is to plug in the values into the Z transformation formula. You can see that these two formulas are the same except for the 3031 and the 4453. Those are the X values in the Z transformation formula. So the lower value, the Z score is negative 1.33, and the higher value, the Z score is 0.54. So we can find the negative 1.33 by finding our table. I've got it on the left here, going down to 1.3 and then across till 0.03, and that is 0.918. So that means that the area to the left of 3331 up there on the curve is just more than 9% of the area under the curve. So then we need to look at 0.54. So we go to the other table where we can slide down, see the 0.5, then go across until we see the 0.04, and at that point we see 0.7054. So the area to the left of 3331 and the green area on that is just over 70% of the area under the curve. But we wanted to know what the probability of a worker paying between those two amounts of health insurance premiums. So now that we have those two probabilities, we can subtract the one from the other to find the area of the green shaded area. And that turns out to be 0.6136, or just over 61% probability that a randomly selected worker will be paying between those two amounts for their health insurance.